Hello everyone and welcome to Network Playroom. This is the second video in the Christmas calendar series and we're going to talk about routing information sources and how the routing table is built. In yesterday's video, we looked at basic routing principles and focused on how the router uses the routing table to forward packets. So now we'll discover how the router learns that routing information. In short, the routing information can get into the routing table in only two ways. It can either be entered manually, which is referred to as static routing, or it can be gathered automatically, which is referred to as dynamic routing. Now let's first talk about static routing. So with static routing, the network administrator is fully in charge of the routing. This is what happened at the beginning of the network world. Administrators used to watch the networks and edit the routing tables manually whenever the topology changed. So static routes reflect the administrator's knowledge of the topology and the policy they want to apply to the traffic going to a certain destination. But there are a number of drawbacks in static routing, and they are obvious. So static routing generally cannot adapt to changes in topology and it doesn't scale. So the administrators would need to constantly keep an eye on the network and change the routing tables in real time. And it may not seem difficult for a network with 5 routers, but imagine what would happen if this technique were used to manage a network consisting of hundreds of routers and links connecting them. It would be impossible. So let's actually look at the network diagram now, and we'll use the same example as yesterday, which was R9 having a loopback interface with the IP address 9.9.9.9 configured on it, and R1 trying to ping that IP address. So let me draw that here again. So 9.9.9.9 attached to R9. And then R1 wanting to ping it. So maintaining static routing for this size topology might look tolerable. I mean, in total, there's 15 routers with few links between them, mostly connected in a daisy chain fashion. And actually, to illustrate this, I've drawn the path from R1 to R9 separately here. It's on another layer which is hidden now, so let me open that up. This one. So that's all it is, one router after another. And I've actually added these networks here to illustrate it with IP addressing so you can get a better sense of what might be configured on these routers. But in order to make this work with static routing, you'd have to tell R1 to reach 9.9.9.9 through R5, then tell R5 to send the packet to R4, and finally tell R4 to forward the packet to R9. So you would have to go like on a hop-by-hop basis and let each router know about this network. And then here, for example, on R1, you would say that to reach this network, go to the next hop of 10.1.15.5, which is the IP address of the interface on R5. And similarly on R5, you would have to tell it that the next hop IP address to reach that network is R4, and so on. But that's not all. So as we discussed in the previous video, in routing principle number 3, so this does not mean the routers know how to forward the packet back. So now you actually have to tell R9 to send the packet to R4, and then tell R4 to send the packet to R5. R5 does not need a static route for the 10.1.15.0/24 network because it is directly connected. So you would have to tell these routers how to get to this network now so that they can reach R1, whose address is 10.1.15.1. So as we discussed before, so R9, you would need to give it a static IP address that is pointing to this IP address as the next hop, and so on and so forth. So as you can see, even with only 4 routers, configuring static routes actually becomes quite tedious. And so what would happen if we added more loopback interfaces? So you'd have to repeat the same process and make sure all routers have their routing tables up to date. And how about if we add more links between the routers so that there's actually more paths between the routers, and R1 could reach R9 using several different paths? So I've also drawn a sketch of that on another layer, so let me open it up. Don't get scared here. So imagine maintaining something like this with static routing. Like, not so nice anymore, is it? That would be quite impossible to do, in fact. Okay, let me hide that quickly. We don't need to look at it anymore. I just wanted to prove a point here. So this is the reason dynamic routing protocols were designed and implemented. So essentially, dynamic routing means automatic distributed network discovery and route calculation algorithms. So instead of doing all this manual work, which I've just demonstrated with static routing, you would simply enable dynamic routing on the routers, and that would do the job for you. So the function of dynamic routing protocols is to exchange information about the networks routers know how to reach. But that's not to say that static routing isn't effective in some cases. For example, when you have a stable topology and don't need real-time adaptation. And in some situation, it is not desirable for all routers to have a complete routing information. So the use of summary routes or default routes, which is technically the ultimate summary route, simplifies network management as it saves the router from having to know all networks. So if we look at this example, again, R1 wanting to ping R9, so technically you could configure a default route here and then again point it to this next hop address, and that would do the job. It would just send all packets to R5, which in this case would be valid if you have this daisy chain topology consisting of 4 routers. I mean, R1 has no other way to send packets, just R5. So it would make sense to have a default route here. Why would you need to know about all specific networks? But yes, to give you a real life example, this is something that I've actually seen in my previous job many times, like a small business network. And static or default routing is sufficient in those cases. So actually, let me use another app to draw a topology for you, because this app has this nice feature. Let me open this one. Has this nice feature that allows me to draw things more neatly. So it would look something like this. So you would have a router or a firewall here. So let me just say router. And then typically a switch right here. And then You might have a server here. Beautiful drawings, by the way. I hope you like it. You can still see all my magnificent skills in action. All right, let's see. So that's a server, and then let me draw some kind of PC or laptop here. So this is more or less what a small business network would look like. I know maybe some of you are thinking of the network design now, like, isn't that a terrible design? Because it has so many single points of failure. We can talk about that another time if you don't know what I'm referring to. But yes, if you're a small business, in some cases, like, that's not one of your priorities, because it does cost a lot of money to implement high availability. So that's why I've seen many networks, simple networks like this one, where you just have one router or firewall, maybe one switch, a server configured somewhere, and then computers attached. Oh, and this is a wireless access point, by the way. This funny creature over here. Yeah, so then you would have the internet here. You would connect to the service provider. Ta-da! I hope you enjoyed a quick view of my artistic skills. So let's go back to this diagram. So anyway, in that small business network that I just drew on the other app, I mean, static or default routing is completely enough in that case. And it doesn't make sense to run dynamic routing protocols. So let's move on. So all routing protocols can be classified as interior gateway protocols, also called IGPs, or exterior gateway protocols, also called EGPs. So IGPs run inside an autonomous system and performed so-called intra-domain routing functions. And this set of protocols includes RIP, OSPF, EIGRP, ISIS, and so on. And EGPs run between autonomous systems. And there are only two EGPs, EGP and BGP. So EGP is deprecated and you shouldn't see it anywhere anymore. And PGP version 4 is now the de facto standard for inter-AS routing, also called inter-domain routing. So the main difference between the IGPs and EGPs is in the goals the two types are designed to achieve. So IGPs are implemented to provide fast convergence within an autonomous system, whereas EGPs are designed to share network reachability information. So which networks are in which autonomous systems, and to permit application of routing policies, influencing the results of the local and remote best path selection algorithms. And all routing protocols share the same basic concept. They exchange messages containing information about the network. They exchange messages containing information about the networks the routers know about. So these messages are called routing updates. And every routing protocol has its own format for routing updates and its own algorithm for exchanging and analyzing them. But this is a discussion for another video. But anyways, information in the routing updates is saved into the routing protocol's own database. And from there, the best paths are chosen and installed into the routing information base, the RIB, or commonly called the routing table, and that is what the router will use to forward the packets. So the routing table contains only the best paths. This is something important to keep in mind. So not every route that the router learned will end up into the routing table. So here's a small diagram to illustrate what I've just described. I have it on another hidden layer here. So let's make that visible. So let's say the router learned routes from all these different routing sources. However, only the best routes will end up into the routing table. So as you can see, this router has learned routes through EIGRP, OSPF, PGP, and static routes. And the best of those will end up into the rib here. So this is what the router uses to forward packets. And when you issue the command show IP route, this is actually what you're looking at. So you would use other commands to view the databases for those different routing protocols. I don't want to get into it too much in this video. We'll look at that later on. But just understand this concept that not all routes that the router learns automatically go into the rib. So they're actually saved into the routing protocol's own database first, and then the best ones are chosen and installed into the routing table. So yeah, here's a question. So how does the router choose the best paths then, if only the best ones are installed into the routing table? And you'll actually find that out in the next video. And I'm going to end this one right here, and we'll continue on the subject tomorrow. So thank you for watching, and I'll see you in the next video.